Yes. So recording. Hello, everyone. This is now the end of the 7th week. So this will be the 14th lecture. Oh my God, I feel like we're BFFs after only 14 days together. It's crazy. But we are going to now start statistics, which we haven't really done yet. I know this is a class in statistics, and it's kind of like, what? Halfway through the semester, and we haven't done any stats? The truth is, what we've done so far is more under the realm of probability and combinatorics, the mathematics of counting, both of which you need to do statistics well. So what's a good distinction between probability and statistics? So a good way of thinking about it is that probability deals with likelihoods. Okay, so when I say what's the probability of an event, I'm basically saying what's the likelihood of an event. Sometimes we get that from previous data, like as we talked about earlier in the semester, if I say something like the probability that it rains tomorrow, this is using historical data where I've kind of looked at all the days in the past, 5 years where it looked like today and saw how many times it rained the next day. And I'm using past data to get a value. And sometimes, huh? I'm going to mute you, Megan. Hopefully that's okay. And sometimes we use just basic common sense. Like if I flip a coin and I say, what's the probability of getting a heads, right? I say, the election distracted me. Is the election today? I don't think the election's today, is it?
It's the debate.
Today is the debate.
It's the vice presidential debate.
Is that, is that an important debate?
Going great.
Who's winning?
I can't.
Winning, really? Is anybody winning?
You can't object.
No one's winning.
I just know that as Americans we're all losing. That's all I know. But
The world is losing.
Yeah. I readily admit that politics is not something that I'm very familiar with. It's not something that really interests me that much. Unfortunately, I'm very just in my books, math and science and things that are. I'm not saying it's a good thing that I'm not interested. I'm just saying facts are that I'm not so much. But I would think that people who are Democrats probably say she's winning, and people who are Republicans probably say he's winning. Would that be a valid conclusion?
Yeah, probably.
So it's probably, very biased towards your own personal beliefs. I would think someone like me would be the perfect person to judge because I have no personal beliefs. I just, whatever happens, move on. I'm just not interested enough to actually listen because math's always there and I prefer to do that. Anyways, I'm not saying it's a good thing. It's it's just who I am. I'm a horrible person. But anyway, all right. So probability is very pure, not always pure in terms of sometimes it's using past data, sometimes it's common sense, like flipping a coin 50-50. Statistics is more along the lines of data collection, analyzing data, displaying data, inferring from your data. Okay, statistics is really, if you had to sum it up, I would say a good definition for statistics is the science of data. There's many aspects to data: how you get the data collection, how you display the data, how you analyze the data, how every little thing about data is all in statistics. So the first thing we're going to talk about when it comes to data is displaying data. Okay, you have your data. Let's say you're trying to determine if a coin is fair. So you roll it or you flip it 1,000,000 times. You're really bored one day, and you decide to flip a coin 1,000,000 times. Now, just be aware that in a day there's 86,400 seconds. So unless you can flip like 20 times a second or something like that, you can't do 1,000,000 flips in a day. But we'll pretend that you are. Okay, you're really bored. You do 1,000,000 flips, and you compile H T H T T H H H, and you write out every single one of your outcomes of the 1,000,000 flips. How many pages do you think that would take to display or to write out all of those H's and T's from 1,000,000 flips? What would you say?
A lot.
A lot. That's a great way of saying it. A lot, correct? Let's say you now have a 30-page book, or maybe even 100-page, whatever it is. It's a lot of pages. And you say, here's my data, look at it. And you give it to someone. And they're flipping through all this data and they see nothing but H's and T's all over the place. It's not very useful, is it? But it's the data, it's what you collected. So there's a difference between the actual data and how you're going to describe or display the data in a way that is useful to the person that you're giving it to. So this chapter is about displaying quantitative data, not like the one I just said, which is heads and tails. Those are not quantitative, those are categories. But ages, heights, incomes, scores, GPAs, these are all things that take numerical values. Yes, so their question?
I'm sorry, I just Googled it and it could be up to 4,000 pages to take up all the flips of heads and tails.
For 1,000,000 flips would take 4,000 pages, really?
Up to 4,000.
Dang.
If you're taking the average of 250 to 300 words per page, something like that. I don't know.
Okay, that's a lot, basically.
Yeah.
Okay. So I think my point is still made that displaying data takes a little skill. You don't just give the data yourself and say, here's their data, but you do it in a way that will hopefully be conducive to someone's understanding of what's going on behind the scenes. So there's two types of data that we're going to be talking about in this course: quantitative data and categorical data. Now, it's important to understand that just because something has numbers does not automatically make it quantitative data. Okay, if someone is 10 years old and someone else is 20 years old, can you, in a meaningful way, average those two numbers? Can you say on the average they're 15 years old?
No.
Why not? What's wrong with that? Don't assume that my answer
Because
is
they're
no.
two separate people.
I know, but on the average, okay, but okay, how about this one? You ever hear the expression, the average household has like 1.5 kids or something like that?
Yes.
Okay, obviously no households have 1.5 kids in them, I would hope. That's a very sick individual who would have 1.5 kids. Like, they'll just chop that kid in half. This is not like King Solomon.
No, the 0.5 is the pet.
No, 0.5 is not the pet. Pets matter, okay? Pets are like...
Pets are two people.
Well, I won't go that far. They don't matter that much. But anyways, when they say 1.5 kids, what they mean is on the average. One house might have one house might have two, but on the average, there's 1.5 kids per house. Okay, it doesn't mean any house has 1.5 kids. It's an average because that's a type of data which it makes sense to average. Okay, number of kids. Those are numerical values. 1 here, 2 here, 12 there, 3 there, 5 there, 0 here, 1 here, 6 there, and so on. You can take those numbers, you can average them, you can do all this math that we've done before with them. It makes perfect sense. Okay, can you average heads and tails? Can you say, oh, I did 1 head and 1 tail, and let's see, H is the 11th letter in the alphabet, J, H, I, J. H is the 9th letter in the alphabet, and tails is the 19th letter. So on the average, I get an M. Does that make sense?
No.
It makes no sense. You can't average categories like you can with numbers. But there's some situations where you cannot average numbers. It makes no sense. Can anyone think of numbers that we use every day? I mean, you might not think about using it every day, but every day we use a certain type of number where averaging them makes absolutely no sense. Can anyone think of one? I can think of at least 2 just off the top of my head. The types of numbers that we use every day where it makes absolutely no sense to average them and get a meaningful answer.
What time you wake up in the morning?
No, if someone wakes up at 7 and someone else wakes up at 8, on the average, they wake up at 7:30. Perfectly fine. Right? On the
What about
average,
a phone number?
phone numbers is a great example where it makes absolutely no sense to average them. Like, oh, I'll take my phone number and your phone number, if we average those phone numbers, do we get anything meaningful? No, it makes absolutely no sense, right? Can someone think of anything else besides phone numbers that are numerical where averaging makes no sense?
Birthdays,
Birthdays. Well, let's take a look.
like 05, 21, 87, like average those numbers up or something.
Okay, well, I would certainly say that if we only talk about the year, like what year
Yeah.
you were born. Okay, so Megan said address. Well, so let me answer what I see here first. I think birthdays might constitute numerical because you can average years, for example.
Oh, yeah.
Okay, but addresses are wonderful, right? I mean, if someone's address is 6738 and someone else's average is like 1529, then halfway in between them you get a number. It doesn't mean anything. Another one is zip codes, right?
Professor, I have a question.
Yeah, go ahead.
So is it that quantitative data can be averaged?
Quantitative data can be averaged and categorical data cannot, or at least it makes no sense to. Like if I see that you're in zip code 90210, you're in Beverly Hills, right? You're on that TV show. So your zip code is 90210. And my zip code is, let's say, 61397. You can't average those two and say, well, if you live halfway in between, that must be your zip code. They don't work that way, right? Averaging them makes absolutely no sense. Correct? So just because you see numbers does not automatically mean that averaging them makes no sense. If averaging does make sense, if you can add them in a meaningful way, in a truly meaningful way, then it's quantitative data.
Oh, okay, that makes sense.
Okay, if you cannot, it's categorical data. And it's no different than something like heads and tails. It's perfectly categorical. Does that make sense?
Yep.
Okay. Now, when it comes time to actually display data, someone else said passwords. I guess maybe PIN numbers would be something better, right? PIN numbers. Your PIN on your debit card or something. That's not really data though, because I guess if you're, if I ask 100 people what their PIN passwords are and they're stupid enough to give them to me, and I average those 100 numbers, that average means nothing, right? On the average, the password is 3627. What does that mean? No, that makes no sense. So that would be categorical. Yes, go ahead.
What about like averaging two people's shoe sizes?
No, that's perfectly valid. If I have 1,000 people, if I'm curious what the average shoe size in America is,
Okay.
I would take 1,000 people, get their shoe sizes, take the average, and that's my answer, right? It makes perfect sense to do that. I might not do it for 2 people because the sample size is small, but if I did lots of people, it's a perfectly sensible thing to do. Okay. So when it actually comes time to do displaying data, we have a different approach for quantitative data than we use for categorical data. They get different types of visual displays. Okay, categorical data is almost always going to be displayed in either a bar graph or a pie chart. Have any of you seen a pie chart before? They're all over the place in books and textbooks and on the internet everywhere. Pie charts are almost, they're kind of hard to define, but they're so obvious once you see them. Okay, and bar graphs also, you probably see. We're going to get into them, of course. This chapter is about displaying quantitative data, so I want to focus on that. But most probably next chapter will be categorical data, so we'll get to that in a minute. Okay, so in this lesson, we're going to learn about displaying quantitative data, and we're going to learn that there's a number of ways of doing it. I've seen pi. I have also seen pi. When I see pi, I don't see pi very long. I have to be honest, it doesn't last very long when it's in front of me. No, Tolaire, pecan pie does not count. It's disgusting. Now, if you said cheesecake, no, it's not really pie. Apple pie, pumpkin pie. No.
Yeah, pumpkin pie.
Okay, now, oh my God.
Cherry pie with ice cream. Yay.
Mississippi mud pie.
That's good.
You say mud pie? Pumpkin, right?
Mississippi mud pie, yeah.
It's like chocolate and whipped cream. It's amazing.
Oh, I think I've had those. But pumpkin
Nice.
pie is still bad. Stop it. You guys are all wrong. Pumpkin pie is the best. Okay. I'm the teacher. That's just the, okay, done. Let's move on. So anyways, you're making me hungry. Oh, Catherine, don't understand something. Nothing makes me hungry. I'm always hungry. Okay. I became hungry on day one and I pretty much stayed there my entire life. That's just how I feel. And oh, coconut cream. Coconut cream. That's pretty good too. Anyways, okay, let's move forward. So when it comes time for for numerical data, let's look at the following. This is what's called a dot plot. Okay, a dot plot is our first oh, lemon meringue. Oh, I'm sorry, I got distracted there for a second. Lemon meringue is good. Oh my god, it's awesome. Anyways, dot plots. Okay, a dot plot is kind of obvious what it is. They're dots, right? Lots of dots. That's why we call it a dot plot. Okay, it's kind of obvious. Okay, basically what you do in a dot plot is every outcome gets a dot. So for example, I'm not sure if this is 4 or 5 because the graph is a little off, but assuming it's 5, 6, 7, 8, 9, 10, yeah, probably 5. How many 5s did I get in whatever, sorry, what's a Dippin' Dot?
Oh my God, are you kidding me?
I'm not kidding you. What's
They're like these
The best
little,
kind of
I
ice.
think they're like liquid nitrogen dots, but they each have little flavors and you just scoop them up and eat them. They're really tiny, but they're good.
Do you guys know what I ordered yesterday? Because some of my other class mentioned it. Let me show you my Amazon order. Hopefully my account information won't be here, but let me show you.
You're
what
getting
I-
Dippin' Dots for your birthday, Professor.
Hold on. Let me show you what I ordered yesterday because someone in my other class mentioned it. Okay, I ordered this yesterday because someone mentioned orange creamsicle Twizzlers.
Oh, those are good.
Okay, so I ordered them.
Holy smokes, I've never seen that before.
I have never seen them either. How do I not know? I don't know. Okay, I missed out. Anyways,
I gotta get that.
so you last purchased this on October 6, 2020. That was yesterday. Okay, Amazon Prime, so worth it. They better be here today. Hopefully they're here now. I don't even know. Let's see. Or how do I track this?
What are your orders?
Go to my orders. You're gonna see what everything I've bought. That's probably embarrassing.
And you
Let's
put
see.
And check the most like, out of the way places around your house. Like mine sometimes
Dad,
have a back gate.
can you go to the door? And my package arrived.
Go get it before someone porch thrifts it.
Yeah,
I
porch
know.
pie.
Seriously, can you? Would you mind grabbing some of my package arrived? Would you mind getting it for me?
Do I need any money for it?
No. It's just sitting by the door. Okay, that's gonna be here very shortly. That's best news I've had all day. Anyways, let's get back to math. Okay, and we'll get back to the Dippin' Dots. I gotta write that down. Dippin' Dots. Hold on. Dippin' Dots. Okay. All right. You gotta try on camera. Oh, I will. Trust me. Anyway, so whatever we're just so let's see what we're talking about here. Different graphs below display the saturated fat content in 69 fast food hamburgers. Data were collected in January 2017 from online nutritional information provided by the fast food restaurant chains. So what we have here is the amount of saturated fat in grams from all of the, I guess, 69 fast food hamburger restaurants, whatever. So there's 69 dots.
Remind me to steer clear of the one with 35 grams.
That's probably the best one. The supersonic burger. The supersonic burger has the most saturated fat. The supersonic burger. Go. Don't judge me. Go.
There's an easy open
Go.
tear.
Keep your class now. Huh?
There's a tear, easy open, perforated.
Blair, don't tell him.
I wasn't paying attention.
He'll struggle.
I'll get it.
Use your teeth. Hey. Hello.
Professor, do a mukbang.
Do a what?
A mukbang.
A mud food?
A what?
Where you eat on camera and you tell us how it is.
Okay, I was planning on doing that.
Oh.
Gross.
Hello, welcome to David's mukbang. Today we're going to be eating some Twizzlers.
Oh, that's good stuff. I got to talk about it, or can you just see the expression on my face and understand what's going on?
You can talk about it and like describe how it tastes and like, I don't
People
know.
chewing loudly as these no, I'm sorry. Oh crap, it is being recorded. Anywho, so when we look at this, we need to review. Okay, when we look at this, we see that the supersonic burger has the most saturated fat. How many grams does it have?
35?
35 grams. Now, a McDonald's hamburger has the least. How many grams does it have? How many grams does the McDonald's?
One, two, one.
Well, I mean, if this is 5, it's kind of hard to tell. Is it 1, 2, 3, 4, and 5 is missing? Is it 1, 2, 4, 5? A better graph would be better, but obviously that one there's McDonald's. Let's say it's 1 gram.
I think number 3 doesn't have any grams, so that's why there's like a space in between.
Yeah, that's
So
what
that
I'm
would be
thinking.
1.
That's what I'm thinking as well. That's what I'm thinking as well. So I would say it's 1 gram. Oh, listen, this one is 35. Sorry, not 1. This is the McDonald's. It's 1. Now, the In-N-Out burger has 5 grams of saturated fat. Circle a dot that might represent this burger. So how many restaurants have 5 grams of saturated fat in their burger?
5.
5. So any one of these 5 is as equally likely to be the In-N-Out burger as any other one. Because there's no order to the 5, right? I just want to have 5. I just want to have 5 burgers that have 5 grams of fat, and I put them up there, and that's it. Now, what percentage of the burgers would keep a person under the government's recommendation of less than 20 grams of saturated fat per day if they also ordered small fries, which have about 5 grams of saturated fat? So let's look at that one. And
So they'd have to order a burger that's 15 grams max.
15 grams max. So $15 grams max. He's laughing at me. So 15 grams or less. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14, 17, 19, 20, 24, 25, 27, 32, 37, 30, 41, 43, 44. All right, it looks like if my counting was right, 44 restaurants would keep you under the government's recommendation of 20 grams or less if you also order a small fries. Now, of course, we all know that when you go to a restaurant, you don't order a small fries, you order a large fries because fries are good. So, and plus, what does the government know? Yes, Hilaire, go ahead.
But it's asking for the percentage.
Yeah, it's at, oh, it is. What percentage? Oh, so it's 44 over the total number of restaurants, which I believe up on the previous slide said was 69 restaurants. Agreed?
Yep.
Yes.
So that's pretty straightforward so far, right? I hope. I guess talking about my Twizzlers is getting everyone so interested that they're focusing on the math. We should do this more often. So here's a ruler drop experiment. A 5th grade class of 27 students conducted a ruler drop experiment. What exactly is it? One student made this dot plot with X's of the student's reaction time in seconds. I guess it's you put your hands like this at the bottom of the ruler, and then someone else lets go. And of course, as soon as they let go, the ruler drops, and they're somehow recording your reaction time in centimeters, which means when you grab the ruler, how far has it dropped? So for example, these are all their answers. The first drop was probably 6 centimeters. The next one, 19 centimeters. Next 2, or at least the next one was 16. And then one of the other ones was 16. They probably didn't make 2 16s, right? They probably did 16 and then they kept going and said, hey, we got to repeat. Let's put another dot by 16. Of course, they also didn't use dots, did they? They used X's. But that's okay. A dot and X is the same thing. But what is wrong with this dot plot? What is the real issue with this dot plot?
The numbers aren't in order. The
The
values.
numbers are not in order, right? They're just kind of all over the place. So it says construct an appropriate dot plot. So we make a axis, and of course we draw a straight line. Mine's beautifully straight. Don't question that. And we also want to have a vertical axis. The vertical axis is always the frequency. In other words, how many times it occurs. And these are the possible outcomes. In this case, it's in centimeters, right? The number of outcomes in centimeters. And what is the smallest number going to be on my dot plot?
1.
1. And how many times did that occur?
Twice.
Twice.
Twice, right? So we have a dot, and then we have a second dot. And then here's 2, and here's 3, and so on. We eventually get to 6, and how many dots do we have by 6? Looks like we have 1 dot because here's 6. Did I miss? Oh, here's a 5, by the way. Right, we also have a 5, and 5 gets a dot. And so on and so forth. I think dot plots are relatively self-explanatory. Would you agree?
Yep.
Okay, any questions on a dot plot? Seems relatively self-explanatory. Now, a dot plot is wonderful because with the dot plot, you get all of your data, right? I know exactly how many times I got a 5. I know exactly how many times I got a 6 and a 7 and an 8 and so on. A histogram is better than a dot plot in some ways and worse than a dot plot in some ways. The bad thing about a histogram is that you no longer have all of your data. Because rather than having each possible outcome, we group them together. So for example, if you look at this histogram on the page, how wide is each group for this particular histogram? How wide is each group?
Two.
It looks
5,
like each one
5
is, well, it looks like each one is 2 because if you look right here, 0, 2, 4, oh,
okay.
actually, no, never mind. This is 10. So it's not 2. I'm sorry. It looks like this is 5 because it's 4 evenly spaced lines. So it looks like each one is actually not 3, but closer to 3 than 2. Well, actually the same distance. It looks like each one is a width of 2.5. Right? Would you agree?
Yeah.
Okay. So the bad thing about a histogram, I mean, the one bad thing about a histogram is that you lose all of the original data. Okay, we don't know where in this interval we landed. We just know that we landed somewhere in the interval. Now, if you need to know what you landed on, then a dot plot is better than a histogram. If you do not need to know what you landed on, usually a histogram is better. But like the dot plot, the vertical axis is the frequency, how often it occurred. And the horizontal axis are the actual possible outcomes. Now, what if you land exactly on a border? You don't want to count it twice. So you don't want to count it both in here and in here. So in this class, borderline cases always go into the bar on the right. But that's a choice that you make prior to making your histogram. There's no hard and fast rule that you always go into the one on the right. It's just in this case, in this class, we'll just say you always go into the one on the right. But just be aware that's not always the case. Okay, so that means between 2.5 and 5, I don't think this is the same hamburger example. Maybe it is because we had some ones above. So between 2.5 and 5, according to this histogram, how many outcomes are there?
8.
8, right? The top is at 8. That's the frequency. That's how many that occurred. So between 2.5 and 5, there were 8 outcomes. How many between 5 and 7.5?
Wait, I have a question.
10.
Yeah, It looks like 11 actually.
Oh, sorry, 11.
Sorry, what's your question?
What does borderline cases mean?
That means what if you land right here at exactly 5? So you're on the border between the left column and the right column. Which one do you go into?
The left?
Huh? Sorry, I can't hear.
So I'm sorry, I just don't get why that one is like all the way over there.
I'm sorry. You don't like, I don't understand your question. You don't get like,
The one that's like all the way over there, like when it says borderline cases go into the bar on the right.
no,
Like
no, not this bar on the right.
Oh,
It means,
okay.
it means if you're on the border, you go to the one in your immediate right.
Okay.
Not all the way over here.
Okay. Thank you.
Okay, I see where the confusion was. Okay, yeah. So if you landed 5, that means you're in this one. If you're at 10, you're in this one, and so on. Okay.
Got it. Yeah.
Okay, so what is the major disadvantage of a histogram compared to a dot plot is that we lose the actual data. And because we lose the actual data, it is a disadvantage, right? I mean, sometimes you want to know it. So Gary, the one all the way to the right is actually an outlier. Well, it's a good question. There certainly seems like to be a downward trend. So on that end, it might not be considered an outlier. If I were you, I would calculate the median. Did we do the IQR and the 1.5 IQR rule in this class? Not yet? Okay.
No.
Okay, so there is a mathematical way of determining whether or not something's an outlier. We haven't learned it yet. Okay, we have not learned it yet. As to whether this is an outlier, it's kind of hard to say. I mean, there's certainly... Yeah, I would say it is because we see lots of them here at low saturated fat, and as we go higher, it becomes more and more and more unlikely. And then, bam, we stop at 30, and then all the way over here at 35 or whatever it is, all of a sudden we have one out of nowhere. This is probably an outlier. And to be honest, I don't know what restaurant this is, but I do want to try it out.
Supersonic.
Supersonic, is that a real thing? Because it sounds great. I mean,
is a
I
Sonic
gotta be
restaurant.
honest. I tried Fat Burger. I had high hopes, and I was a little disappointed. I was expecting.
That burger is really expensive.
Money is no. Yes. What I can't make it disgusting. Yeah, does not worth it. Well, I don't know. I'm not a big fan of In-N-Out. I know it's almost sacrilegious to say that here in Los Angeles.
Not either. I am
Shake Shack.
I like Shake Shack.
That's one.
I like Shake Shack.
Frosty Queen.
Which one?
Frosty Queen.
I have tried Fat Cells. Fat Cells is good. I have not tried that one. If you have recommendations, email them to me. I'll try one every week per your
Frosty
recommendation.
Queen is pretty good, but they're also a bit expensive.
Again,
But they're pretty good. But my favorite is In-N-Out.
In-N-Out, so commercial. Okay, whatever. Doghouse. Now we're talking. Anyways, let's keep going. All right, so this is an education, guys, not just for math. This is an education for where to eat in this city, because I'm starting my diet in a couple weeks. I don't know if did I show you this? My sister? I show you my sister?
Yeah, you showed us.
So I figured my birthday's in a couple weeks. So what I'm going to do is I'm going to, get all the things I can in now, and then start the diet in a couple weeks. Bring food to class, guys. We should all be eating at the same time. Okay, I'm stuck eating dolma. What the hell is dolma?
Oh, that's good.
Well, I don't know what it is.
Professor, I have a question.
Please,
Go ahead.
please.
How much saturated fat are in those Twizzlers?
It says total 1 gram. 1 gram saturated fat.
That's
1
it.
gram. 1 gram. Now, it says there's 8 servings per container, so I will have 16 grams. for my total. but it's 1 gram. So I answered your question. Anyways, let's keep going. So how many burgers had less than 5 grams of saturated fat according to this histogram? Less than 5 grams. Never ever bag on your grandmother's dolma Armenian roll.
Hilaire, you're absolutely right. Absolutely right. Dolma is incredible. Never bag on
I don't
Dolma.
like it.
I don't know what it is.
It's just sometimes my grandma cooks it a little bit too long because she's getting a little bit old. So sometimes she forgets to cook it for too long, and it gets a bit dry. But her dolma is really good.
Well, I will be the judge of that. I think
I mean,
we
you're
have to have a dolma and Dippin' Dots party sometime.
Yeah.
It's
Oh,
basically
sorry, we
there's
forgot
two
to
different-
explain it. It's like at least my grandma's is like pumpkin with like squash, and it's got rice and meat mixture. But some people also do the rice and meat mixture wrapped in grape leaf. So yeah.
You had me at pumpkin. That's all I can say. Okay.
Yeah.
So let's answer
It's
the question.
very comfort food. It's very comfort food.
Yes,
Yeah, it's really good.
that's basically all I eat. Okay, so how many burgers had less than 5 grams of saturated fat, according to this histogram? So we got to find 5, of course. Right, we got to find 5. 5 is, as we said, right here. We know that the border goes on this one. So if I want how many have less than 5, what is it? How many is it going to be according to the histogram?
That 8?
That's 8, right? What about 30 or more?
1.
30 or more is 1. What about 30 or less?
1, 2.
You have to add up all of it?
You'd have to add up all of it. But you got to be very, actually, that's a bad question. What if I said 5 or less? Let's make it a little easier. What if I said 5 or less? What would the answer to 5 or less be?
1.
8 plus 11?
Well,
Isn't it? Because you have the 5 is a part of both the 10 and the 8. So you have to do some sort of subtraction.
well, it's actually, if you think about it, it's actually impossible to answer.
Okay.
Oh, because you don't know
Where
how
are we
many
getting
are.
this 8 and 11?
Huh? Say again?
Where are we getting this 8 and 11?
The frequency on the y-axis. So like the
Oh,
first
okay.
whole bar is equal to 8. The second whole bar is equal to 11.
Okay, sorry, I'm blind.
It's okay. That's okay. You have your other 5 senses. You're still good. So here's the thing. We don't know how many of these 11 are actually equal to 5. Maybe they all are. Right? Solaire. The more the merrier. That's all I can say. Okay. So we don't know how many of these 11 are actually 5 and how many are more than 5 but still in this range. So for all we know, it's anywhere from 8 to 19. It's not a question that you can answer based upon what you're given. But you know what? If I had a dot plot, I would be able to answer that. Right? So that's the advantage. That's the one advantage of a dot plot. Okay, is that you actually get all of your data. All right, so a different version of the histogram appears below. Okay, this is the same data, but it's a very different histogram.
Yeah, they changed the y-axis.
Well, they didn't change they changed the scale, right? They certainly changed the scale, right? Before it was every 2, or I think, right? Every 2, now it's every 5. But they did more than that. What's another major difference that they changed that's more important than the Y scale?
The X scale?
What about the X scale?
The burgers are more clumped up together, like they're in larger groups.
That's the thing. Now each interval has length 5. Instead of before where each one was 2.5, now they're clumped up in groups of 5. Right? Which is further away from the dot plot where they were in groups of 1, each individual outcome. Now they're clumped up in larger groups, which means, well, actually, I don't want to answer what it means. I want to ask you what it means. Which version do you prefer? The first one, like this, or this one?
The first one.
And why? And why?
The first one, because it was a lot more clear. I think it had more of the data shown, whereas this one is just lumping everything together, basically.
Okay. Well, it's good. I mean, basically, if you look at this, we see a downward trend, a little gap, and then we have this one over here, right? If we do this one, we still get the downward trend. We still have a little gap, and then we have this one. So that in and of itself isn't really a change. But the big change is we know exactly how many are between 2.5 and 5, and how many between 5 and 7.5, and between 7.5 and 10. When you group them together, you lose some information, right? You're getting further away from the perfect dot plot where you have every piece of information. You're going in the other direction, right? Now, statisticians, you can't, I mean, you could, but you shouldn't lie when it comes to the data. However, the way you display the data, you can demonstrate different patterns. So quite often what they do is they take their data and they come up with a way of displaying it that supports whatever their opinion is. Someone else can then take exactly the same data and display it in a completely different way that supports their opinion, right? So part of being a good statistician is being able to recognize how the data is being displayed. Oh, I hit the wrong button, sorry. How the data is being displayed and used to support, whatever hypothesis the person has, and whether or not you can skew it that way. Okay, does that make sense what I'm saying so far?
Yeah.
So in the last few histograms, the vertical axis displayed the frequency. The frequency is literally how many times each one occurs. But quite often, instead of the frequency, we're going to have the relative frequency. What's the difference between frequency and relative frequency? Anyone know the difference between frequency and relative frequency?
Is it a proportion? Kind of?
Well, so relative frequency doesn't tell us the number of times it occurs. It tells us what percent of the time it occurs, the proportion of time that it occurs. Okay, does that make sense?
Yeah.
Okay, so it's the same histogram. If you look at it, it's exactly the same shape. The shape does not change when you switch from frequency to relative frequency. What changes is the y-axis. The shape, the bars, the x-axis, exactly the same. The y-axis changes from how many to percent. Why is that important? Well, sometimes you might want to compare two different histograms. What if sorry, question?
Yeah, what did you say the difference was? The relative frequency?
Frequency is how many? 8 times it occurred, right? That's how many. That's the exact amount of times it occurred. Relative frequency is the percent of time that it occurred. Oh, this occurred 12% of the time. Because if I'm comparing two different data sets and one's a lot larger than the other, the frequencies are going to be a lot more for that one than for the first. Of course, it's like you compare how many people walk on the street in New York at different times of day versus Nebraska, right? New York and Manhattan is going to be, the numbers are going to be so much bigger, right? But to get away from that, we can look at proportions and say, well, at 1 o'clock, that was in both cities, that was 23% of the population, or whatever the case may be. You can compare things a lot easier sometimes with proportions than you can with relative frequencies. Okay, so let's take a look at this one here. When examining graphical displays of quantitative data, look for answers to the following question and always include units when applicable. Without units, answers are wrong. The histogram gives the age at which 315 dogs were diagnosed with diabetes. Very sad. First, what is the source of the data? Where did this data come from? So that's here. It's A.G. Popol et al. Frequency of, I don't even know what that word is, and whatever. So this is some
Endocrinopathy.
Yeah, I didn't need you to embarrass me by being able to pronounce it when I couldn't. Okay, so Larry, just go back to your whiteboard and don't talk anymore. Okay, so so we have this magazine, this journal of some kind. It's the source of the data. Why does it matter what the source of the data is, by the way? Why does the source of the data matter? Huh?
Because it's,
Credibility.
yeah, it could be a part of the data that's just from that location and not like the entire global world.
It could be, but it could also be that some journals are more reputable than others. Right? I mean, you want to get your data from the National Enquirer or from the Wall Street Journal. Now, I'm not saying the National Enquirer is not correct. That's for you to decide. But the point is that not every source is equal, right? Right? Remember, as Abraham Lincoln said, not everything on the internet is true. Right? So now, so what is the source of the data? It's this journal of, if you want to know how to pronounce it, ask Tolaire. Next, what are the variables and what are the cases? That is, what was measured and who or what was it measured on? The variable here is age. That's the thing that varies from case to case. What are the cases? The 315 dogs. Case 1, case 2, all the way through case 315. Now, does the distribution have any unusual characteristics, such as clusters, gaps, or outliers?
Doesn't it kind of look like a bell-shaped curve?
A little bit, right? A little bit. It's not too skewed from that. So in this particular example, I don't think there's any clusters, gaps, or outliers. You know, I mean, it's low here on the sides. It grows up in the middle. This looks very much like a bell curve, which is as perfect as it gets when it comes
Professor?
Yeah.
Can you repeat what the variables and cases were?
The variable?
Yeah.
What was measured? In this case, it's the age.
And then the cases.
The cases are what it was measured on, the dogs themselves.
Okay, that makes sense.
Case 1 through case 15, or case 1 through case 315. Does that make sense so far? Now, in general, when we look at the shape, there's essentially a few different general shapes that we're trying to look for. One is called a skew to the right distribution. It looks normal until it's not on the right side, right? Very bell curve shaped, and then it's skewed. The tail is creating the skewness. This one here, skewed to the left. This one is wonderful. It's normal, which means bell. Uh-oh, there's a chat. I missed it. Someone's laughing. So what was said? Hold on. I got to look at this one. Oh, that wasn't it. Huh? Tag yourself. I'm symmetric, but not normal. What the hell is she talking about? All right. Not so there. You're the life of the party. Okay. I'm not normal and unsymmetrical one. What is going on here? Megan, set them straight. Okay, so this one is symmetric. Symmetric means it's kind of a mirror image on both sides of the center, that if you reflect it over, it lands on itself. And normal is a synonym for a bell curve. Okay, so when you hear normal, that doesn't mean, oh, it's not unusual. No, normal is very specific. Normal means it's a bell curve. So this one here is symmetric. It's a perfect image over the center, but it is not normal. It is not a bell curve. Now, I don't know what situation in real life would have a distribution like this, where it's a lot in the middle, tapers off, then grows again, and then tapers off. So Larry, you have an idea? I'd love to hear this one.
Probably COVID.
Probably COVID. Well, what do you mean? Like, let's think about it. Let's think about this. COVID affects mostly the old, right?
Okay.
So I would think it's a skewed left distribution.
Oh, I mean like all the reports that say that it's up and then it's down and then it's up and then it's down and then
Oh, I see. Well, let's see. I don't want to get into the politics of anything. So, because I never know the opinions of my class. So it's hard to, I can joke, I can make a joke that's taken seriously by someone and get into a lot of trouble. So I'm gonna lay off politics. That's the one thing that I'm gonna try to stay away from. But most humans are not symmetrical unless they pay. Oh, wow. Okay. That escalated. Okay, so here are the things that you want to, um, woo, blushing. Okay, so here are the things that you want to ask when it comes to distributions. One, where is the center of the distribution? Okay, where is the distribution centered? Okay, in this case, it's not hard to see where the center is.
Could you
In
say
this-
it's kind of skewed or no?
I'm sorry?
Could you say that it's a little bit skewed or no?
This one?
The one from the top, the above.
This one?
No, the problem before. If you're referring to that one.
This one?
Yeah.
I don't know. I mean, the center up here is around 10. And if we go 10 to the left or 10 to the right, it kind of tapers off pretty, I mean, it's not perfectly normal, but I would say this is fairly normal.
Okay.
So one thing you want to ask is, where is the center? You can ask, what is the spread? How spread out is the data? And we're going to learn various measures of calculating spread. And if there are certain patterns, you're going to want to try to explain why. You know, so if you did come up with a situation like this, you try to explain it and say, well, babies, let's say it's with age. Babies are not really affected, but teenagers are. Then people in their 30s, not so much, but people in their 50s, that's the worst. And then people in their 70s, not so much, but 90s, yes. And then once you get to like 100, you're fine. I don't know. I can't really think of anything in particular that would have this pattern, but maybe somebody can. I don't know. I can't, but maybe you can come up with something that kind of fits that pattern. That's the thing about distributions, right? It's not like one distribution rules them all. Different situations require different distributions. Some are normal, some are skewed, right or left, and all different types of situations. So here, this histogram shows the violent crime rate for the 368 California cities with at least 10,000 residents. Would you say, just by looking at this histogram, how about when people have midlife crises? Well, let's take a look. 50, lots of people have a midlife crisis. Babies, not so much. Teenagers, I don't see why it would be why it would jump, you know, at that time. And then,
Or we could call it when you have an existential crisis in your teens, when you have a midlife crisis, and then when you're older.
so retirement age,
Maybe.
your midlife.
It's like your quarter life crisis, right?
Maybe.
Yeah, there you go.
Okay, quarter life crisis, midlife crisis, 3/4 life crisis. I don't give a shit anymore, right? So that could very well be that. Hey, why the hell not? That sounds great. If you actually did a study on what age people had their first real, you know, mental crisis about what am I doing with my life? Okay, where am I going? It might look like this. Okay. All right, great job. There you go. I'm surprised you didn't put it on your whiteboard. Okay, anyways, so here we have a histogram. Here we have a histogram. The question is, would you say that this is a normal histogram?
It's skewed right, isn't it?
It's very skewed to the right.
Yeah.
I think everyone is in their middle life crisis right now, LOL, no matter the age. Oh my God, look at that. Adorable. Hello.
This is Bobby.
Bobby.
Hi, baby.
You're so cute.
Sorry for the distraction.
That is never, between that and food, everything's okay. All right, so Los Angeles has a violent crime rate of 719 per 100,000 residents. Place an X on the bar where Los Angeles will be located. So here we have, again, here, let's move this out of the way. Okay. This is the violent crime rate for 368 California cities with at least 10,000 residents. Los Angeles has a violent crime rate of 719 per 100,000 residents. Place an X on the bar where Los Angeles would be located.
Professor, is the 500 on the x-axis supposed to be like 500,000 since it's per 100,000, or is that just
Well,
500?
the x-axis is violent crime per 100,000.
Mm-hmm.
So if I was, let's say, if I had 503 violent crimes per 100,000, I would land in this bar.
Got it.
So Los Angeles has 719 per 100,000. Which bar do they land in? Here's 500. So tell me when I get there. First bar, this one, this one, this one, this one, this one, this one, this one.
That one.
There.
Yeah.
Well, here's 700.
Mm-hmm.
Here's 700. The
And-
7 to 800.
And here's 800, right? So it's certainly smack dab inside that bar. Make sense?
Mm-hmm.
How do I keep hitting the wrong button? Jeez. Okay. All right. So here are the violent crime rates for the 86 California cities with 90,000 or more residents. Oakland has the highest crime rate. Estimate this rate. If you had to give an estimate for the violent crime rate for Oakland, which we're told has the highest crime rate, which
Is
one
that
would it be?
300 to 400?
Well, 300 to 400 would be, oh, you're looking at this, right? Well, remember, this is how many cities fall into this region. Oakland is just one city, right? Oakland is the city with the highest rate. So which city, the city with the highest rate would be in which bar?
Wouldn't it be the last one? That's around the 15.
Yeah, it will be the last one. Exactly. Right? It will be this bar right here.
Mm-hmm.
So if I had to give an estimate for how many or for what the crime rate is for Oakland, given the fact that the left edge of the box is 14 and the right edge of the box is 15, then what would be the best crime rate to use? What would be the best approximation based upon the fact that it's in this bar whose left edge is 1400 and whose right edge is 1500?
1450.
Excellent, 1450. In the absence of any other information like a dot plot where I have the actual value, you just take the one right in the middle. Okay, because unless you know for whatever reason which way to lean, it's your best guess. How does this distribution compare with the one for cities of 10,000 plus? Well, if we go back to the one with 10,000 plus, the highest one was 1550, right? On average, whatever this city is. So it's a little less. But in general, they're not asking for the highest. I'm sorry. They're asking how the distribution compares. How does this distribution compare with this distribution? Do you see any major differences there?
Yeah, the frequencies on the second one are more sporadic. They're more all over the place than the first one. The first one kind of has more of a pattern. It decreases as it goes, as the crime increases.
You mean as you go further to the right? Is that what you mean? I'm sorry. As you go further to the right?
Yeah.
So say that again, please. I didn't quite understand what you said. Say that one more time.
So in the first graph, the numbers, they slope down and decrease as you go further to the right.
Okay.
When you look at the second one, the numbers are more varied.
So it's like up, down.
Yes.
Kind of a little more fluctuation in the beginning. But this one also has up, down. Right? Up, down, or up. So up, down, and then tapers off. This one also has a little fluctuation, right? I don't know. Maybe it's a judgment call. This kind of question's a judgment call. Some people see some things, some patterns that other people miss. I personally don't really see much difference. They're both right skewed, right? The general shape of this is up and kind of skewed that way. Yes, still there?
The frequency for this graph, the range of the frequency is smaller than the previous.
Okay, but that's, remember, this is 86 cities, correct?
Right.
So the frequency is how many cities? This one here had 368 cities, right? You're going to have a lot more cities when you're considering 368 of them than when you have only 86 of them.
Okay.
Right? The heights are the cities, right? How many cities are from here to here? If you're only considering 86 cities, you should expect the frequency to be lower.
Okay.
Now, if you compare their relative frequencies, what proportion of them were there, then that would be a much better measure. Is it 20% for both, 30% for both? Because then you're ignoring the actual sizes and you're looking just for percentages.
Okay.
Okay. So, anywho. Okay. So the next one is called a stem plot. So we have two so far. We have dot plots and we have histograms. The next one is called a stem plot. A stem plot is kind of like a histogram and it's kind of like a dot plot. It's kind of like a hybrid. A histogram can display an enormous number of values. We had 368 values here on this histogram. And there's no reason why we couldn't have 3,000 values or 3 million values, right? There's no reason why we couldn't, correct? Okay. For a stem plot, you can't really do lots and lots of them, kind of like a dot plot, because you're actually listing all of your data. The question is, how does that work? So here's what a stem plot does. In this particular stem plot, we have the number 3. Then we have another 3. And then another 3. And then a 4, a 4, a 4, a 4. What comes next? 5. Then 5, 5, 5, 5, 6, 6, 6, 6, 6, 7, 7, 8, 8, 8, 8, 9. What comes after 9?
0.
10.
Kansas 10.
10, 10, 11, 11, 12, 12, 12, 13, 14, 14, 14, 14, 14, 15, 15, 15, 20, 26, 35. This guy here is the first digit of every one of them. And all of these are all of the second digit. So 1, 5 represents the number 15. Dave's single cheeseburger from Wendy's has 13 grams of saturated fat. How would you display 13 grams of saturated fat? It would be that number right there, because it's 1, 3. What if I had a new burger with 34 grams of saturated fat? Where would I put that?
Put a 4 in that spot.
Put a 4 right here.
Yeah.
34. Notice that the first 0 only allows 0 through 4, the first 5 digits, and then a second 0 for 5 through 9. 0 through 4, 5 through 9, 0 through 4, 5 through 9, 0 through 4, 5 through 9. So a stem plot is kind of like a histogram, and it's kind of like a dot plot. Histograms are really the best for lots and lots and lots and lots and lots of values, whereas the stem plots and dot plots really only work for a small number. Does that make sense?
Yeah.
Again, hard to describe in words, but once you've kind of done an example, it's fairly self-explanatory. Then you can have back-to-back stem plots. In a back-to-back stem plot, there's no example here, but in a back-to-back stem plot, you have your first digit here, and then on one side you have some data, and on the other side is a different data. So I might have something like this. I might have 2 or 20. If we ignore the last digit, because they're all zeros, I might have 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, and I don't have to go past 10. So let's see what I have here. 24, okay, right there. 29, right there. 53, right there. 52, 72, 750, 75, 220, 270, 630, 750, 850, and 1040. And then if I wanted to put a second one to compare it, the second one would have numbers here. So if I had 280, for example, and the other one, I would put an 8 right here, and it would be 280 and so on.
Professor,
Yes.
wouldn't you do McDonald's versus Burger King back to back?
Oh, I didn't read what they wanted. I just thought they were all one data set. I wasn't looking at these. You are right. So I screwed that one up. So let's erase all that. And oh, so Talia, put in your whiteboard. Here, I'm gonna spotlight you. I'm gonna spotlight you. Can everyone see her?
Okay.
Hold on, no, not on the whiteboard. You can just do it on the because we're almost out of time.
Oh.
So can everyone see her? How do I make? I don't know how to make. I don't know how to make her bigger. But did everyone see what she did? Because I'm too lazy to do it myself. Yes, no. Anyone have a question?
So Larry, your McDonald's is on the right, right?
Yeah, McDonald's is on the right, Burger King's on the left.
Got it.
Does that make sense?
Yes.
Not really.
So you know what, we
Makes
are
sense to me.
we are out of time. We'll do this first thing next time. We'll finish it up quick and then we'll move on. And don't forget, next week there's a quiz on Monday after class, not during class, on chapter 7. And we'll then jump into in class. We'll finish up this stuff and move to the next chapter. So I don't know about you guys, but I got my dates tonight. So I'll see you all later. Have a great night, everyone.
Thank you, Professor.
Yeah, you're welcome. The quiz is due next Wednesday. Yeah, you got 48 hours or something for it. You know, I'll give you time for it.
Wait, you're giving us our quiz on Monday?
I'll give it to you on Monday after class and do by Wednesday type thing.
Okay, thank you.
Thank you.
You're welcome. You're welcome.
Thank you. Hope you figure out what the Dippin' Dots are.
I'm certainly looking into it. All right, I'm gonna stop.
Professor, I had a question real quick.